So hello everyone, welcome to the third lecture of this week. So we are talking about distribution semantics, and we had already discussed what is the generic framework of distribution semantics, how do you build models by taking different sort of targets and context, and how do you fill up all the entries in a matrix. Now in this lecture we will talk about some applications for distribution semantic models. Also, how do I compare similarity across two words, and then we'll move towards some structured models of distribution semantics. So starting with some application. So let's talk about this problem of term mismatch that we see in the case of information retrieval. So what is the problem? So in information retrieval, the user is giving a query that is in terms of certain words that he feels are describing his information need, and so he's trying to so the system is trying to match this set of keywords to all the documents that are there in the repository, and by doing this matching they're trying to find out what are the potential documents that can be returned to the user. Now what is one problem here? So it might happen that the particular concept that the user has in mind, the user is expressing by using certain words, but the documents have the same concept using a very different word. So they are the words are similar on the semantic label, but on the surface label they are two different keywords or two different words. So this is called a term mismatch problem, and one of the key issues in information retrieval is how do we solve this term mismatch problem. How do I find out that the user typed this particular term, but he might also be interested in the other term that is semantically similar, but on the surface form it is different. So let's see an example. So suppose there is a user query, insurance cover, which pays for long-term care, and it might happen that the relevant document that contains the answer to the user query may have words like Medicare, premiums, insurers, etc. that are not directly provided in the user query. Now one question is, how do I find out that these documents that contain some similar words are also relevant to this user query? So for this task, one can use distribution semantic models for query expansion. So query expansion is one of the techniques that is used for this term mismatch problem. So idea is that the user has given a query with certain words. Can I try to find out some other words that are semantically similar to the user query words? If I find out some words, then I append those words to the user query, and this is called the expanded query expansion process. And now I give this expanded query to my search engine and then retrieve the documents. So now what we will see in brief, can we use our distribution semantic models for this problem of query expansion? So what is the idea? So once user gives a query, we reformulate it using the terms that are relevant or that are related to the terms that are already there in the query. Find out some related terms and try to use that to improve the retrieval performance. So how do we find out the related terms? So firstly, I have the query terms that the user is giving, find out what are the distribution vectors, and take a functional combination of all the distribution vectors and obtain the expanded query. So suppose the query has 3 terms, find out what are the related terms to all these 3 terms in the distributional sense, and make a linear combination of all such possibilities and give the expanded query to the user. So how will it look like? So suppose the user gives a query like catastrophic health insurance. So what are you doing? So in your distributional vector, suppose you are finding out what are the terms that are related to each of the 3 terms: catastrophic, health, and insurance. Okay, so what will happen? So user has given these 3 terms. And suppose you were using words as context, so different words were there, WI, WN, and for each word, so you were computing what is the co-occurrence. So it can be, say, PMI value. What is the PMI between catastrophic and W1? So like that you are computing for all the words. So now what you might do, you might say, okay, what are the words that are associated with all the 3 words, so that are having high PMI values. So one way is you just add all the PMI values, PMI q wi for all words q in my query. Okay. So for each word wi, I compute a score like that. What is the PMI of query? One of the query word with this word wi and add over all the query words, and then I can sort it, and maybe I can normalize it with respect to the highest term. So what will happen at the end of that? I can sort these scores and find out what are the words wi prime etc. that are very much related to the query terms. And all this we have already covered. How do we compute these scores? Once we have this scores, I can compute this simple formula and find out what are the terms in a decreasing order. So this is one particular way, but you can have any other sort of functional combinations. So this is simple addition, but you can have multiplication and other sort of functional combinations also. So suppose we do that. So what happens to the actual query? So this is my actual query, catastrophic health insurance, and if I try to use this technique to find out some other related terms, I get terms like this. So I have terms like Surtax, HCFA, Medicare, HMOs, Medicaid, HMO, beneficiaries, premiums, and so on. Now, so these terms are taken by from a news corpus, that is US news corpus. So there are certain terms that are relevant to the US medical system. So what you are seeing in these expanded terms? So some terms are like broad expansion terms. So that means if you look at maybe some WordNet or some other thesaurus, you can find out such kind of similar terms. So you will say, okay, Medicare, beneficiaries, premiums are some broad expansion terms. So they are related to the query. In addition, you also get some very specific domain terms, like here HCFA, that is a US domain term for healthcare financing administration. Similarly, HMO for health maintenance organization, HHS. So these are very domain specific terms. So if you know that your query is coming from a certain domain, this approach can be very helpful to also find out terms that can be used to expand the query and are also domain specific. Okay, so let's take another example. So I am showing here some track topics. So track is a text retrieval conference. So they organize various competitions for information retrieval. So they are actual queries from the track data. So you have a query like ocean remote sensing, and when you use this method, you can find some other terms like radiometer, Landsat, ionosphere, CNES, altimeter, NASDA, meteorology, and so on. And again, as we saw in the earlier query, there are some broad expansion terms like radiometer, Landsat, and ionosphere that are connected to the query, and there are some domain specific terms like CNES and NASDA here. So this is one very nice application of distributional semantic models. You have some existing query, you want to match it to some document. Why don't you expand this query by using some related terms? And this is the idea. And this you can use in general for any matching task. You are having different text data and you are trying to match these. So try to find out if they are somehow related on the semantic label using distribution semantic models, and use this idea to find out if they are similar or not. Now, so once we have computed the distributional semantic model, so I have the vectors for different words. Okay, so different target words, I have the vectors. Now, how do I compute the similarity between different words? So it depends on what is your representation that you are using for computing the semantics, or what is the vector representation. If it is a binary vector, you will use different sort of similarity methods than if it is a real valued vectors, or if it is a probability distribution, you will use a different sort of similarity metric. So as such, the framework allows you to use any of these vector representations. So let us see if you are using any of these, what kind of similarity methods you can use to compute similarity between two words. So let us say so I have words x and y, and they are denoted using some binary vectors. So as such, any sort of distribution you can also convert into binary vectors. So how do I compare, or how do I find similarity between two words where the representation is binary vectors? So for binary vectors, we have some standard methods like using dice coefficient. Okay, so what is that? 2 times intersection of x and y divided by length of x plus length of y. And what do I mean by this? So x and y are binary vectors. Suppose x and y are binary vectors, and let us say the size of my vector, the dimension are, say simplicity is there 19 dimensions, okay, and my x is 1 1 1 1 in the first 10 dimension and 0 0 in the rest 9 dimensions. On the other hand, y is 0 in the first 9 dimension and 1 in the last 10 dimensions. Okay. So now I have two vectors x and y, and I want to compute the similarity between these two vectors. So suppose I am using Dice coefficient. So the formula is 2 times x intersection y divided by length x plus length y. So this is the length of x intersection y. Now what is x intersection y? So that is only one element, okay. So x intersection y has only one element, that is 1. So this will be simply 1, 2 times 1. Length of x, how many ones are there? Okay. So you will not take the length of the vector, because otherwise it will be the same for everything. Everything will have the same size. So length of x means how many entries are 1. So here it will be 10, for y also it is 10. 10 plus 10, so this will be 0.1. Okay. So now this is okay if you have the binary values. Suppose you do not have the binary values. So suppose my values are like, my x could be 0.3, 0.5, 0.7, 0.01 and so on. So if you want to use these measures, so one simple way could be convert them to binary. And now converting would mean you would put a threshold, that if the value is below this threshold, then you put it to 0, above the threshold you will put it to 1. So suppose here threshold is 0.05. So what you will do, this will go to 0, this will go to 1, this will go to 1, this will go to 1, and here you will check whether less than 0.05, then go to 0, if greater than, then go to 1, like that. So you can convert any such vector into binary representation and then use this Dice coefficient. Now are there some other methods of computing similarity also? So we have Jaccard coefficient and overlap coefficient. So Jaccard coefficient is x intersection y divided by x union y. Now what is the difference between Jaccard and Dice? In what scenario Jaccard will give a different value than Dice coefficient? So let's try on the same example. So I am using the Jaccard as x intersection y divided by x union y. Okay. So now in this case, what is x intersection y? This will remain as 1, only one entry is 1. And what is x union y? Now x union y will contain all the elements. This will be 19. So what you are seeing for the same two vectors, Dice gave a value of 0.1 and Jaccard gave 1 by 19, that is closely 0.05. So this gave much smaller value. Okay. So why is that? So you are seeing here, if there are very small number of shared entries, Jaccard further penalizes. Okay. So that's what you are seeing here. There are only one entry common among 20, so Jaccard is giving further penalty. Now what will overlap do? So overlap is x intersection y divided by minimum of xy. So can you think of a scenario where overlap can become 1, but say Jaccard will not become 1? So this will happen when one of x and y is completely included in the other. So let us take a different case. Suppose my x is 1 1 1 1 1 0 0 0 0 0 and y is 1 1 1 1 1 1 1 1 0 0. Okay. So in this case, what will be the Jaccard? It will be x intersection y divided by x union y. So this will be 5 divide by 8. And what will be overlap? This will be x intersection y divided by minimum of x and y. Okay. So this is again 5, and what is minimum for x and y? Again 5. This will become 1. So that is, if one of the vector is completely subsumed by another vector, overlap is 1. Okay, and that will not happen in Jaccard or Dice coefficient. And similarly, if there are a small number of shared entries, Jaccard will give a smaller value. So that means depending on what kind of similarity you want to use, you can have either Dice, Jaccard or overlap. Suppose in your task you want to find out if one of the words is completely subsumed by another, you will use overlap and not Jaccard. Okay, but if you want to see some other criteria, you can choose one of the 3 methods. So here, so what you are seeing, Jaccard coefficient penalizes a small number of shared entries, while overlap coefficient uses the concept of inclusion, whether one of the entries completely included in the other one. Now this is if your vectors are binary vectors. Suppose there are real number values, so like x and y. So let's say there's a n-dimensional real number values. So then you can use simple cosine similarity or Euclidean distance. Okay, so you can use cosine similarity and Euclidean distance. Now what is the difference between the two? If my vectors are not normalized, cosine similarity and Euclidean distance are different. Okay, but if they are normalized, they will be the same, and they will give the same sort of ranking, and that you can do it as a very simple exercise. If they are normalized, they will give me the same sort of ranking between the similarity of vectors. Now on the other hand, suppose my distributions are probability distributions. So I am denoting different vectors as probability distribution in my space of the context vectors. So then how do I compute the similarity? I will use different measures that are used for computing similarity or distance in the case of probability distribution. So what are the common measures? So you can use KL divergence. Yes, so that is sigma I pi log pi by qi. So KL divergence is asymmetric. Okay, so if you use divergence between p and q and p, they may come out to be different. So that's why there is a symmetric divergence also, that is information radius. So p and p plus q by 2 and q plus p by 2. Find the KL divergence between these and add those. That is information radius. And also you can use a very simple formula like L1 norm. So you have pi qi, find out the L1 norm. So what is the difference between pi minus qi? Sum over all I. So that is, you have different sort of representation and you can use different similarity matrix. Now, so let us talk about what are the what are some other sort of distribution semantic models that also try to use some specific structures in the sentences, and we try to motivate them using this example. So that is, what is the difference between an attributional similarity task and a relational similarity task. So what is attributional similarity? So that is, I am given two words like dog and wolf, and I want to find out how similar they are. So similarity between dog and wolf will depend on how much their attributes are similar. That's why it is called attributional similarity. And by using distribution semantics, how do we capture that? What are the other words they are co-occurring with? Are they co-occurring with similar sort of words? If they are co-occurring with similar sort of words, they will have a high attributional similarity. And what is relational similarity? That is slightly different. That is, now I am talking about pairs. So that is, I have two pairs A, B and C, D. Are they relationally similar? That is, how many similar relations that they have. So example would be like one pair is dog and bark, second is cat and meow. So now dog and bark, do they share similar sort of relation as cat and meow? So this is a different type of task. Okay, and so that's why the first one is called attribution similarity, how much the attributes are similar among the two words. Second is called relation similarity. I have the pair, the relation between this pair, does that hold also for the other pair? Okay, and this also gives rise to many analogy testing tasks. So A is to B, yes, C is to what? So we will see how do we extend our distribution similarity or semantics model to also capture all these cases. Now for that, we need to talk about a different sort of matrix, and this will be called pair pattern matrix. So till now we are talking about target context matrix. So let us see if we can use a similar idea for building a pair pattern matrix. So what do I mean by this? So here the row vectors will correspond to various pairs of words like maison stone and carpenter wood, and the column would be various patterns in the sentences these words occur with. So like here, X cuts Y, X works with Y, etc. And then you compute the similarity of rows to find similar pairs of words. So now, so what do we mean by this? So till now what we were doing, we had words like dog, cat, and I was finding out these representation in various contexts. So I am finding out vectors for dog, vector for cat, and trying to match these. Okay, and this was my simple attributional similarity. So now what am I doing? I am trying to compute a similarity between pairs. So now my rows are different pairs. So like the pairs can be, say, dog, bark, cat, meow, or it can be like here, maison, stone, carpenter, wood. So like that there can be various pairs. Now these are my rows. Now what do the columns denote? Now columns would be various patterns. So pattern could be like X cuts Y, X works with Y, and so on. These are various patterns. Now what are X and Y? You can think of these as my patterns XY. Sorry, pairs XY. Now how will I fill this matrix? Simple way would be, I have X and Y. X can take value like maison and Y can take a stone for a given pair. Now I will go through my corpus and see what are the various patterns in which these words co-occur with. So suppose there is a sentence, maison works with, or mason works with stone, or carpenter works with wood. Let's take a sentence, carpenter works with wood. So here, so I have a pattern, X works with wood, X fits for carpenter, Y fits for wood. So I'll say okay, there is a +1 here. Similarly, there will be all sorts of patterns here in which X and Y can occur, and I'll fill which pair occurs with what patterns. So now this is my pair pattern matrix. Pair pattern matrix. And then I can, once I have this matrix, I can compute which pairs occur in similar patterns, and then they are called relationally similar. They have similar relation at the other pair. So we can talk about the extended distributional hypothesis that was given by Linen-Pentel. So what is the idea? Patterns that co-occur with similar pairs tend to have similar meanings. So here we are talking about in terms of our columns. So here suppose what they are saying, if a pattern P1 and pattern P2, if they co-occur with similar sort of pairs, then they are giving similar sort of meanings. Okay, and therefore I can use this matrix to compute semantic similarity of patterns also. So I can find out semantic similarity of the pairs, also the patterns. So suppose I am given a pattern like X solves Y, and I want to find out what are other similar patterns as X solves Y. How will I do that? I will first enumerate all the possible patterns that can occur with X and Y. Then I will find out all the possible pairs, how many times they co-occur with various patterns. So I will fill this matrix, and then I will find out for this pattern like X solves Y, what are some other patterns that are having similar pairs as X solves Y. Okay, and whatever patterns like X is solved by Y, sorry, Y is solved by X. Okay, suppose it occurs with similar pairs as X solves Y, I will say that this and this are similar, and that will be the idea. It's like here, Y is solved by X, Y is resolved in X, and X resolves Y. So what we will find, all these patterns occur with similar pairs, so they can be also called similar. Now So now what is one thing? So for dealing with this pair pattern matrix, words will not be my basic context units. So how do I capture and represent this sort of information, like x solves y and y is resolved by x? How do I capture this information? So for that, I'll need a formalism that can capture semantic relations and also various syntactic information can be captured. And for that we will go back to our dependency based formalism to capture this kind of information. What is the idea? So let us say I have a sentence like the teacher adds a red apple. So I can first formulate a dependency graph for the sentence. Now I can use these dependency relations to say that only some sort of dependency relations are interesting and others are not interesting. Okay, so for example I can say that eat is not a legitimate context for red. Okay, all the eats and red co-occur with a very small distance context window. I can say that okay, the relation direct object and a modifier together do not form a very nice context. So I will not use this co-occurrence. So I can be selective in choosing what kind of co-occurrence information I will use and what kind of co-occurrence information I will not use. And I may also give them different sort of weights. So for example, I can say that the object relation connecting eat and apple will be different than the modifier relation connecting red and apple. Okay, so this relation direct object and a modifier can be different relations. So till now what was happening? I was only seeing if this word co-occurs with this word or not. So now we have started talking about in different terms. This word co-occurs with another word in this context. Okay, so with using a direct object relation, with using an adjective modifier relation, and so on. Now, so from the parser I can get all these relations. So how do I further use those? So we will say that to qualify as a context, a word must be linked by some interesting lexicosyntactic relation. So what do I mean by lexicosyntactic relation? A good dependency path should exist between the two words. So in simple terms I can only use a single edge between two words. Okay, but in general you can also talk about larger length of edges between the two words. So let's take it simply for the simple paths of length 1 between two words. So what will I do? So let us say I have a sentence, the virus affects the body's defense system, and I get this dependency pass. Now from the dependency pass I can extract the various triplets like system, direct object, affects, body, possessive, system. So these are the various tuples I can extract from my dependency graph. So I will have things like this: system, direct object, affect, and so on. Now how do I use those for my structured model? So let us try to have a look. So we will have words like system, dobj, and affects. Yes, and I'll have many such tuples. Now how do I use those for my distribution semantics? So there are actually many ways you can do this. So one simple way would be just forget dependency information. So that means you will have system, affects, and so on. So that is, you are going back to your earlier DSM where you were not using the structure. So this you can again convert into that kind of model. The word system is here, and what is the co-occurrence with the word affects, and you will have one, and so on. This is one way. So where you forget the dependency information, but that's not what you wanted, right? You wanted this information for some reason. So another option could be I combine dependency information with the context. So my context is now structured. So that is, I'll have system and my context is direct object of the verb affects. Okay, so these are my context now. So then I can represent system in this context, direct object of affects, direct object of other verbs and subject of these verbs and so on. Okay, so now you see immediately my dimensions are different from here. Here I had only words, here I have verbs and some relation together. But I am going back to the same sort of matrix format, and still I cannot do this dog is to bark and cat is to meow. I cannot do it here. Now what is some other sort of representation from here that you can gather? So other could be, I combine these two in my rows, this become my target and this become my context. So that would be, third would be, so like system and affects come in my target and direct object is my context. So now I can talk about my pair matrix. So I have system and affects, these are my pairs, and patterns right now are only dependency relation, direct dependency relation, direct object and subject and so on. Okay, and this is the general framework, pair pattern. Now here we are talking about only very simple paths of length 1. What is the direct relation between these two words? You are free to choose a higher order path. It can be, okay, there is a path of length, direct object and subject and so on, and use that as your patterns here. Okay, so that can help you to capture all these things like x solves y. So you can also use what are the different words that occur in between these two words. If there are some other words occurring, that can be your one of the patterns. So here you have complete freedom of choosing what are your patterns. So these are simple dependency graph for simplicity, but you can choose any other patterns that you would like. These patterns can come from maybe dependency graph, they can come from the word co-occurrence, what are the different words that are occurring between these words and so on. And then you can compute similarity between various pairs. Okay, so now quickly, so we have this data and I can use that to get this information or the other sort of information or the third sort of information that we saw. Now let us see one simple application, like how do we use that to find out selection preferences of the verbs. Now what do I mean by selection preferences? Now different verbs for their different arguments like object, subject, they prefer a particular type of noun, and this information is useful in many tasks like dependency parsing. So for eat, I want to know that eat will prefer only certain sort of nouns as objects. Okay, you can eat only very specific things. So how do we compute this selection preferences for verbs? So we have seen that from a parsed corpus I can compute these vectors like virus and system. I can put them in this space, how many times car occurs as an object of carry. Okay, so you are carrying car, you are buying car, you are driving car, you are eating car, and you are storing car and flying car and so on. Okay, so what are the number of times, and this is some normalized values. Vegetables, how many times are they carried, bought, eaten, stored and so on. Okay, so this you can compute from your corpus once you have the parse. So this gives you some sort of representation that what kind of objects come into, that can be used, what kind of words that can come as object of the verb buy, what kind of words will come as object of the verb drive and so on. Okay, but suppose you want to build a prototype, that is in general what kind of words can come as object of the verb eat. From the corpus here, one simple thing I can do, I can find out which words have a high value. So I know vegetables can be eaten, biscuits can be eaten, so they have a high value. But suppose I want to build a prototype for a new word, that word that is not occurring in the corpus, how likely it is to come as a object of the verb eat. So what will I do? So what is a simple method? So I would say, okay, let me find out what are the words that are having a high weight in this dimension. So I know vegetables, biscuits, fruits, etc. will have a high weight in this dimension. Now my hypothesis will be words that are similar to these words, like vegetable, biscuits, can also be eaten. Now how do I find out words that are similar to vegetables, biscuits and so on? So for that I'll build a prototype, that is, okay, what are these words? So these are words that can be carried, bought, stored, right? So that means any other words that can also be carried, bought, stored might also be eaten. Okay, so then I will find out all the other words that have high weights in these dimensions other than eat, because whatever is having high dimension eat I can easily capture here, but what are the other words that are having high dimension in all these high weights in all these other dimensions? That also can become my prototype. So what will we do? Suppose I want to compute the selection preferences of the nouns as object of the verb eat. I'll take some top n words like vegetables, biscuit that have high weight in this dimension of object eat. Then I take the complete vectors, so that is of all these top nouns. So this will be words like that can be consumed, bought, carried, stored, etc. Now this becomes my object prototype. Now given any noun, try to match it with this object prototype, and you will see that how likely it is to come as a object of the verb eat. And that is a generic method of finding selection preferences of the word noun for any noun to come as a object or a subject for verb. So we talked about how do you extend your distribution semantic method for using structured models. Okay, a lot of work, again a lot of research has gone into this domain. So we have only touched the basic intuition, and I hope if you need this idea, on your own you can think about how do we use different sort of interesting context, interesting targets, and solve various problems. So in the next lecture we will talk about another very important interesting idea, that is what are word vectors and word embeddings, and how do we obtain them from the corpus, and what are different tasks that they can be used on. Okay, so I'll see you in the next lecture. Thank you.